Hey guys, so today we will be covering two random number generators, Rng Loot and Rng LCG. All of the stuff that we go over will be in a data pack in the description. And this is basically just a really good random number generator within a range or just any number, and it runs very quickly. So for example, I have in 1, the first in is 1 and the second in 1 is 5, so out is going to be a number between 1 and 5 randomly. So random number generators have been around for a while. You have your classic dispenser. Put a dispenser down, gives you 1 out of the 9 items. You also have the one that I used to use, which clearly is it's pretty bad compared to this one. This was back in 1.12 that we mainly used it, and I just never bothered seeking out a new one. But basically, you just have 2 area effect clouds, and you randomize the bits. So in a binary number, you have a bit, and each bit is worth like a different value. So you have 1, 2, 4, 8, 16, 32, 64, and it just keeps going however many bits you have. So this is a 1, 2, 3, 4, 5, 6, 7 bit number. So our number has 1, 2, 6, 8, 1, 2, 4, 8, 16, 32, 64. And the biggest number you can have is 127. And so basically, with the previous number generator that I used, we basically just were like, okay, so if we pick a random area effect cloud, one of the 2 of them. So on the first one, if it happens to be the left guy, we put a 1 here. If it's the right guy, then we put a 0, so we don't add. So then that's really all you do. So then it basically generates a random sequence of 0s and 1s here, and then you add them. So this is 1, 2, 4, 8, so 1 plus 8 is 9, and your random number is 9. And that's basically how it did it, and then it used some math to lock it to a range, which was slightly biased, so it was not perfectly uniform. Blah, 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 blah. That one is old, that one is dead, sucks, okay? The problem with that is there's 2 entities. You're using kill, you're using summon, you're using a selector for every single bit. That is intensive. That takes up a lot of CPU, and if you're doing things, if you want to randomly generate a number very quickly, you don't want to do that, especially for things like my RPG where I have bloom, which is where bullets are randomly shot at slight random rotations, and that random number needs to be generated quickly. So the next logical step or thoughts for where to get another random number generator is from loot tables. So this is an Rng loot table, and so basically loot tables have a certain criteria thing called amount, and you can pick min and max. And this basically just means it picks a random number between the min and the max and does that to the place. So a lot of times people do that with count. So you'll see from way back when, you'll see loot tables that have like, give me an apple, but give me 1 to 3 apples, and it'll give you 1 to 3 apples for the count of the apples. So we can use this and combine with our data get and our execute store from 1.13. So basically this is just going to put a golden hoe, and it's going to give you one that has attributes, and it's going to give you just a fake attribute that has an amount between -2. This is the max integer value in the negative direction, and this is max integer in the positive direction. So it gives you a number between these 2 bounds. And basically you just play this loot table into a chest or into a shulker box, and now you have the hoe with the data. So that's basically all I do in this function here. In here. So loot is going to, there's a definite block, and it plays the RNG, it puts the RNG thing into the container 0. So that just means that this first slot right here is constantly being just replaced each time you run the loot command with a new randomly generated golden hoe damage value, and you store the results, math out, and you grab that attribute. So if I do function RNG loot, you'll see a number that is very big most of the time, randomized, which is fine. And of course, then we have a method to lock that to a range, which we'll go over the range locking later. But basically, I just want to show you that this is a random number generated from a loot table. Loot is nice and all, that's cool, but that's not as efficient as possible. So I thought that would be the best, but some people on the MCC told me otherwise, and they also showed me this loot function. But yeah, so I thought that was like, okay, boom, done, video, perfect. But then I was shown something even more insane, because this kind of stuff even I don't really study or go over, so I don't really know about it. But anyways, so this is good and all, but the problem is you have to have an actual block at a certain location. So you have to have a block in a force loaded chunk there, which is kind of annoying. And then you also need to have this loop command and a data get command, which those are pretty heavy commands. You don't want to have to do them all the time or a lot. So it's fine. It's only 19 commands if you didn't see, but there is a better way. So that's where the LCG comes in. LCG is linear linear congruential generator, and so we'll go over that in a second. But basically, it's able to generate a random number generator using LCG, and it takes 3 commands, and those 3 commands are only scoreboard commands. Take a look at this. Boom, literally just 3 scoreboard commands. And actually making it is a lot simpler than understanding why it works. So that's why I started working on this thing, and then VDV Man on the MCC helped out and finished it and made it actually like run so you can see all the results the way it should be. But yeah, so I'm getting the same thing, like random numbers, kind of random numbers, from just running this function of only 3 commands that are scoreboard commands instead of data gets and loots, which is a lot better. So an LCG is kind of what your computer uses sometimes. You basically have a seed or a place to start in this crazy function that looks wild and just points everywhere. And you have a seed to know where to start, and you're going to go to the next number each time. And what's random is really the fact that the seed, you don't know what that seed is. And the way that we get the starting point seed is using a area effect cloud. So when you first load the Datapack ever, only one time, it summons an area effect cloud, grabs its UUID value, which is going to be dependent on the world and other factors, and stores that onto a number. But a much smaller version of it, because it's a lot more bits than we need. And it just does that once in the setup. It doesn't have to do it every time. And then from there on, we can hop around. So let's kind of discuss and visualize how that works. So this is similar. This is basically how it works. So when you have, we went over this before, but when you have an integer number, right? Okay, so this is just an 8-bit number, right? So there's 8 bits of zeros and ones, right? That's how your computer works. So let's say that all of them are 1. What happens when I add 1 to it? Where does it go? What you'll find is it actually overflows. All these become zeros, and you have a 1 out here, but you don't really know what to do with that 1. So you wrap back around. So when you go above the maximum number allowed to be held, you end up somewhere back at the beginning or somewhere else within the range of values that are acceptable. So basically what we do is we take a number and we multiply it by a very, very big number. This number is really big. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 1 billion. So we multiply the number we're at by 1 billion. And when you do that, the number is going to be somewhere. It's still going to be, you may think that it's going to be like, what's 1 billion times 5? That's 5 billion. But it's not actually going to be 5 billion. Since we're an integer, we have to be somewhere within the range. So it's going to go, you can imagine it going up to 2 billion and then wrapping back down and finishing up its movement to the point where it's from negative 2 billion back up a couple to get to the total distance of 5 billion. Okay? Of course, most of the time we are multiplying like 1 million times 1 billion. So where that ends up, I couldn't even tell you, because it's crazy. And then we also add a pretty large number to it, 12,000, just as an extra variable to throw in there. So it makes it go a little bit further even. And what we end up with is a sequence of numbers that seem fairly randomized. So the first dot here And let's pause the animation. So all we're doing is simulating this this math equation. Your value times A plus C is your new value. Okay, so your value is here. You multiply it by the big number, you add a little bit to it, and that's going to give you this value, your next value. Okay, so 0 is going to be 6 to the power of times 10 to the power of 7, and the next value, 1, is going to be 2375 times 10 to the power of 8. And your third value, your second value, well, technically your third, your fourth, your fifth value's down here, 6th, 7th, and it ends up just jumping around like crazy. Now that would seem almost like there is an order to it, but oh, I don't have it anymore. But if you just do that, if you just multiply 0 times it and 1 times it, then it just becomes like a slanted line. The reason we have so much craziness is because we take on the first value, we take 6 times 10 to the power of 7, this value right here, and then we multiply that number by we plug that into the equation. So we plug it in for x, and we get the new value of being somewhere crazy in a weird place. And then we take this new number here and plug it in for x, and then we jump back around and end up here. So that's why it ends up being all speckled. And this is finite, this is definite, but technically the finite amount of times that you have to run the amount of times you have to run the LCG before you get back to where you started is an insane amount. Actually 2 to the power of 31 approximately, times 2. So you have to run the LCG a lot of times for you to start seeing a repeat, and by then you probably won't be able to see the repeat. So this number here, S, is basically your seed. This is where you start. So right now, look in this equation. You see X, you see X, right? Technically, this is X to the power xn. This is xn minus 1. So this means you take the previous, you multiply it by A, you add C to it, that becomes your new. Or really, I guess x to the n and x to the n plus 1. But what is x to the n initially? What's my first value for x to the n? Because you could start from 0, but if everybody started from 0, then everybody's second random number is going to be the same as their first random. Like, everybody's random numbers are going to be the same. So if I start from 0, then when I run it on my Minecraft, I'm going to get the same sequence of random numbers that you do when you run it on your Minecraft, which is not random. So what we do is we grab the UUID and we make that the starting point. So this slightly randomized value of UUID that's kind of dependent on when you spawn the thing and what world it's in, that number that is highly dependent on the player is used as the starting point. And that is what the seed is. So in this situation, my seed is thousands, millions, a billion. My seed is 1,050,000,000, right? Now my seed is over here. Look what it does to the dots. So my answers, my next random number is going to be totally different from your next random number, because my seed is somewhere totally different from your seed. And it doesn't take a lot to make it go insane. Let's go from this value to just one different. Look what one different does. Compare. You have that, and you have that. So even just being one off makes it significantly different. So that's kind of like how this works. There's a bunch of math on Desmos to get the graph working, because they don't allow recursion the way that Minecraft allows recursion. Like, it's simple in Minecraft, but it's difficult to show on a graphing calculator, basically. But yeah, so this just shows all the points that it's picking each time you play the random number generator. Imagine this going all the way to the right instead of looping back to the beginning. It just keeps going on for 2 billion amounts of values. Okay, so now that that complicated explanation is out of the way, that is basically how the LCG works. All you need to know necessarily is that when you implement it in Minecraft, you just have to take the previous value, multiply it by a big number, then add this little constant to it, and make that the output. And when you come back, that number will be used here for the next multiplication. And boop, 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 done, 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 easy. So you get a big number. Now, you may argue that, hey, that's not super random, But I mean, there is math to prove that it's random, but we're going to do a little math to prove that it's random right here. So we're going to pick a range between 1 and 5, and we're going to do LCG first, and basically what this will do is it'll show us the outputs, like how many we have. So I'm going to do reload, and I'm going to do that, and I'm going to put this on the side, and you'll see it's running the loop X amount of times, and you can see just how random it is and whether it's uniform distribution. So this just basically runs 1,000 iterations, and then you can see like that the numbers even right now are very close to each other, which means that it's fairly uniform distributed, meaning that my chances of getting 1 is the same as my chances of getting 2 or 3 or 4 or 5. And that's definitely what you want from a random number generator. This is everything I need from a random number generator. So hopefully it's everything you need. I don't necessarily expect you to just take this data pack and use it in your world. I would be totally fine with you just taking the LCG range, the UUID reset, and this last part that I'll show you next, and just throwing it in, changing the name of the function references, and using it in your data pack. That's what I do. But anyway, so you can see that these numbers are fairly close. The biggest discrepancy is 26, which is not unreasonable per se. It is random. Yeah, so that just kind of proves that it's fairly uniform distributed random number generator. And there's no pattern to this. You can run this dist function multiple times, and you'll see each number have its turn at the top, and there won't be a certain order to it. Now, in terms of how the range works, how the random range works, because this just gives us a huge random number if I do what we already showed it. So in terms of how the range works, it's a little bit complicated and a little bit simple. If you know what the percent equals function is, that's modulus. So if I take 10 modulus 3, then that does 10 divided by 3, and you can't, that normally will be 3.33333, but instead it's 3 remainder 1. So this remainder is what we keep, the 1. And you can basically create a range function for a number to take a number like 1, 2, 3 and make it between 0 and 2 using the modulus. But the problem is when your number is very big, like 1, 2, 0, 0, 0, 0, 0, 0, and you do the modulus of, say, 5, well, now that 5 perfectly divides into it, and your answer is 0, because there is no remainder. And even if we throw a 1 in here, we're still going to get 0. If we throw a 2 in here, we're still going to get 0. The only thing that can change that is if this digit changes, and that's less likely to happen than one of these other digits. So that's why modulus alone is not a very, it's how can I say this? It's biased towards smaller numbers because they're more likely to divide into the whole. So there's a way to fix that using the next int function. It's kind of stripped right off of like Java's implementation. So we have to get the range, so basically how many numbers there are. So 1 to 5 is going to be a range of 5. Okay, and then we have to get this new variable called m1. This is going to be used later, and then we play this next int. So the next int is kind of interesting. It's basically this function from Java, or I think Java, yes. And it's implemented into Minecraft, but we really only take this part. There's a much more elegant representation of everything you see here in the Phi Datapack by, I think it's a couple people like VDV Man. Of course, the Phi Datapack, it's a lot harder to just take the files and strip them, but they'll probably be a better implementation than mine in terms of being mathematically accurate. But I am just doing simple, easy to explain, easy to see everything, easy to show you guys, and easy to steal and use in other places, if I'm being honest. So basically what you need to do is you need to use this, we're basically kind of implementing this for loop mainly. So we're grabbing a random number, then we have to take you saving that random number to a temporary variable to implement this little parenthesis part. So you get the percent of the random number, which is this right here, and then you do the random number minus that answer, so that's this right here. Then you add m1 to it, which is right here, And then you do the extra thing, because since it's a for loop, what's your condition? If this number is less than 0, then you loop again. So if the number result is less than 0, you loop again. And surely enough, this will give you your uniform distribution, like what I just showed you in the thing. There is some extra stuff over here that has to do with like the bound and stuff. They're like kind of extra criteria, but I don't use it because it's just like a bunch of extra commands that didn't seem to be as big of a deal. There is some things with like atrophy or something like that with the when using the LCG, but I'm just not bothering with it at the moment because this was the simplest and most copy-pastable implementation that I could make. Anyways, so you have, in conclusion, you start with a seed. The seed is then multiplied by a huge number and thrown somewhere else on a list of negative 2 billion to positive 2 billion, whatever an integer can be. And then that value is then that value is kind of like locked to a range, but it makes sure that it's not screwing up with that whole case that I showed you. And if it is screwing up with that whole case that I showed you, then you're going to rerun the random number generator and get a new random number and do it one more time. But most of the time it only has to run through it maybe 2 or 3 times, I think only once actually. Let's see, 11, 10, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, I think it only runs through it once most of the time. But sometimes it does go a few more commands to run a second loop, but that's fairly rare. So yeah, just keep it the format that it is. If you want to strip this into another data pack, you have to change what this function location is, and you have to change what this function location is, and you have to change, that's it. That's really all you got to do. And you have to make sure that you have that UUID reset coded in. So I guess just take init. If you take init, you'll be good. Delete this part right here if you don't want to use the shulker box, and you're good to go. You don't need dist, you don't need this. That's just testing it. Anyways, that's pretty much it. Hopefully you guys found this random number generator useful. It's the best one I've seen so far. Uses only commands that are scoreboard types, which makes it incredibly efficient compared to the others. Anyways guys, thanks for watching, and I'll see you in the next one. Peace.